Right, so welcome everybody. Thank you for joining us. So today it's our pleasure to hear Daniele Oriti, who will tell us about tensorial group field theories, quantum geometry, and emergent cosmology. Please.
Yeah, thanks, Mark, for the introduction, and Mark and Etera for the invitation. So yes, I'm going to talk about some recent results and the more general story about the tensorial group field theories. So let me first of all introduce a bit the framework, at least the key ideas. So the starting point is the idea that quantum space-time can be described as a superposition of discrete structures, simplicial complex in most of the implementations of the idea. And here you see a generalization of matrix models which have been quite successful for describing two-dimensional Riemannian quantum gravity. So somehow you see this class of models as quantum field theories for some candidate fundamental degrees of freedom underlying space-time, out of which space-time as we know it should emerge in some approximation. And the basic point is to have an action, a field theory action for a field, which is a tensor. And the key input is that the interaction of such a field should possess a characteristic non-locality or combinatorial nature in the way the arguments of the fields are paired together. Now, this is the key common ingredient for a large number of models that have been studied, and you see some variety and consequent confusion in the literature about names, because different criteria are using for calling specific models in different ways. So you hear about tensor models, tensorial group field theories, tensorial group field theories. In all of these models, the basic object is a tensor, but the domain of the tensor changes depending on the model, and sometimes with this changes the name assigned to the model. The interactions are combinatorial non-local in a sense that I will clarify in a second, that as I already anticipated, but the specific form of the combinatorics changes from one model to the other, and sometimes the name changes. And then other features can be implemented in the propagator, in the properties of the tensor, in the properties of the interactions. And again, this can lead to use different names. Here, I'm calling tensorial group field theories the general formalism, and then I will specify my discussion to what I will call quantum geometric models, which are models with a much stronger relation to loop quantum gravity, spin-found models, and simplicial gravity path integrals in a way that I will try to clarify. So let me give you an example. The simplest example to get the idea of the combinatorics, of the combinatorial non-locality that I anticipated, is a tensor model for a rank 3 tensor with indices taking value from some finite set, for example, a finite group. And the geometric pictorial interpretation of the tensor is as describing a triangle with the 3 indices labeling the 3 edges of the triangle. And the interaction pattern chosen to represent the way 4 triangles, so 4 fields, are glued together along common edges, here common indices, which are identified, to form a 3-dimensional cell. So a cell 1 dimension higher than the cell associated to the tensor. Here, a tetrahedron, a 3-simplex. So this general combinatorial pattern of a non-local type has furthermore a general consequence, which is that the Feynman diagrams of these models are then dual to cellular complexes. And that means that when you expand perturbatively the partition function of the theory, you generate a sum over cellular complexes of all topologies resulting from just gluing together the cells corresponding to the interaction, to each fundamental interaction. And in the example I gave earlier, you have tetrahedra forming the basic interactions. And so in this type of tensor model, you're going to have three-dimensional simplicial complexes, gluings of tetrahedra as Feynman diagrams. Now, for quantum gravity models, it's important to have at least a link to lattice gravity in this perturbative expansion. And in the simplest model, the amplitudes are purely combinatorial. There's no additional degree of freedom than combinatorics. And so the link to discrete gravity can only be given in terms of a dynamical triangulations type model. So you assume the simplicial complexes that are generated to be equilateral, and then you end up with the definition of the dynamics as the sum over equilateral triangulations. And you can relate the amplitudes to the classical gravity action discretized a la Regge on an equilateral triangulation. In richer quantum geometric models, you have a much more intricate but also more interesting relation to discrete gravity that I will discuss in a second. Already at this stage, and for all the models in this general formalism, within this general formalism, you need to make sense of this sum over Feynman diagrams, so this sum over simplicial complexes. And a number of results have been obtained to ensure that we can do that. We can control, through some additional labeling, the topology of the Feynman diagrams that we generate in the perturbative expansion. And we can actually control the perturbative expansion, for example, defining a large N approximation. And then a lot is known about this class of models, but already these ingredients are crucial for the renormalization of the more interesting, richer quantum gravity models that I will discuss in a while, in the context of tensorial group field theory renormalization. But really a large number of other results, both in physics and mathematics, and beyond quantum gravity, have been obtained for this general formalism, for this general class of models on the basis that I just illustrated. So here I focus only on quantum gravity applications. And what is going to happen is that the combinatorial structure is of a very similar type, but the connection to gravity is richer at the level of Feynman amplitudes, because the triangulations that you generate are not going to be equilateral anymore, are going to have additional degrees of freedom summed over in your quantum dynamics. And there will be instead a closer link to lattice gravity path integrals and spin-fold models. So let's give a look at these quantum geometric models with this richer relation to canonical loop quantum gravity and spin-fold models. So the basic idea is that we can describe the geometry of a simplex using group theoretic data. And at the classical level, this arises first from the realization that we can discuss in 4 dimensions, in case in which the basic building blocks are tetrahedra, the geometries of an individual tetrahedron using 4 vectors normal to the triangles, which are forced to be lying on the same hypersurface, so orthogonal to some normal n, and summing to 0, to mimic the fact, to encode the fact that the 4 surfaces to which each of them, to which the 4 of them are associated, all lie in the same 3-dimensional hypersurface, as a tetrahedron should do, and they're close to form a closed cell, as a tetrahedron is. Under this condition, the 4 vectors that we can use to describe the classical intrinsic geometry of a tetrahedron are in fact vectors in R3. And then one notices that R3 is in fact isomorphic to SU2, the algebra of SU2, as a vector space, and can then associate a classical phase space to a single tetrahedron given by the cotangent bundle of 4 copies of SU2 as a group, therefore introducing conjugate variables being group elements valued in SU2. They had the interpretations of a discretized connection with the SU2 values. So this is the classical phase space we can associate with tetrahedron, on which then we impose the closure and the additional geometricity constraints. And then starting from this building block, one can imagine constructing extended structures, extended three-dimensional triangulations by gluing together tetrahedra, identifying boundary variables. In fact, there is another more covariant description of the same geometry, which uses instead SO31 Lorentz, the algebra elements, and Lorentz group elements. So one can describe the same intrinsic geometry and extrinsic geometry of a single tetrahedron, either using the cotangent bundle of SO3 or SU2, or the cotangent bundle of the Lorentz group. In general, for the class of models I'm going to discuss, there is an underlying phase space for a single quantum, a single entity that is given by the cotangent bundle of a group manifold, to which we impose constraints. Now, at the quantum level, one can quantize such a phase space, so the space of geometries for a single tetrahedron, and arrive at a Hilbert space for a tetrahedron, one representation for which is just L2 functions over the group manifold that we used at the classical level. And again, on this basis, one has to impose constraints, impose geometricity of our data. Furthermore, for states in such Hilbert space, one can provide different representations as functions on the group, that's the starting point, as functions of the algebra, that's like working directly in terms of the intrinsic geometry data of the tetrahedron. Or you can expand by Peter-Weil or Plancherel in terms of representations of the group. Once you do that, you recognize that what you're dealing with is the Hilbert space for what in loop quantum gravity is called a single spin network vertex. And there is a lot of interesting quantum geometry already at this stage, but it's not the part that I want to focus on. The next step is to take this Hilbert space for an individual tetrahedron and construct out of it a Fock space, because we were interested in a field theoretic characterization of the kinematics and dynamics of a universe made out of such building blocks. So this Fock space allows for a second quantized language to describe all geometric operators that describe the geometry, intrinsic and extrinsic, of an arbitrary collection of tetrahedra so quantized. And I give an example here, which is the total volume for a collection of such tetrahedra, just summing over the contribution from each of them with the volume operator for each tetrahedron given by the quantization of the classical phase space I introduced a couple of slides ago. Right, so again, then the same story that I introduced as a general feature of this class of models applies. You define an interaction that corresponds, for example, to take 5 such tetrahedra and gluing them together to form a 4 simplex. So that the interaction has to keep track of how you identify the individual arguments of the fields to mimic the combinatorial pattern of a 4 simplex. Now we really have a field over a group manifold, which is the second quantized counterpart of the wave function associated to an individual tetrahedron. And as in the general case, again, we can expand the quantum dynamics in perturbation theory and end up with the sum over simplicial complexes four-dimensional simplicial complexes for the class of models I discussed, weighted by some Feynman amplitude. And now, thanks to the additional data, group theoretic data that I introduced, the amplitude can be shown to be always given by some spin form model, so some covariant version of a loop quantum gravity type dynamics for spin networks, or in a different basis, and equivalently as a lattice gravity path integral in group and Lie algebra variables. I don't enter into this, but I want to clarify the connection to spin form models for those of you who are a bit more familiar with spin form models. So a spin form model is defined by amplitudes you can associate to any spin form complex, so which is a cellular complex labeled by representation data, plus some way to organize such amplitudes. For example, a complete definition of a spin form model can be given by summing over the complexes through the perturbative expansion generated by a tensorial group field theory. And this is very generic. In practice, what happens is that for any given spin form model, so for any assignment of amplitudes to the various type of cells you have in a complex, an amplitude for the vertex dual to the highest dimensional cell and amplitudes to the lower dimensional cells, you can find a corresponding choice of action, therefore kinetic kernel and vertex kernel for a tensorial group field theory, such that the Feynman amplitudes of such field theory match the initial spin form amplitude. And the advantages of this, apart from being a complete definition of a spin form model, is that you have field theoretic tools, approximation tools in particular, to go beyond the perturbative definition. And so beyond the definition of a spin form model as a sum over complexes and access directly a non-perturbative regime. We're going to see an example of this later on. Concerning the relation to quantum gravity, to loop quantum gravity, this can be seen at the level of quantum states, and I want to spend a few minutes on that. So I've already emphasized that the building block, the single quantum of a tensorial group field theory for such quantum geometric models can be understood as a single spin network vertex, which is in fact a sort of a building block for generic spin network states in canonical loop quantum gravity. In fact, you can go beyond and you can show that the loop quantum gravity Hilbert space associated to a single graph can be faithfully embedded in the tensorial group field theory pre-Fock space, so before you impose symmetrization. But then from such a pre-Fock space, from such shared degrees of freedom, in tensorial group field theory, you move on to define the full Fock space, but the full Hilbert space of canonical loop quantum gravity instead is quite different. And in a word, one could say that the difference lies in the need in canonical loop quantum gravity to incorporate more continuum space-time ingredients since you're coming from the canonical quantization of the continuum theory. But to summarize, what happens is that although the Hilbert space associated to any individual graph can be faithfully embedded in the tensorial group field theory Hilbert space, the way the two formalism, canonical loop quantum gravity and tensorial group field theory, deal with states associated to different graphs is different. The orthogonality relations are different, and moreover, in the tensorial group field theory case, there's no imposition of any type of cylindrical equivalence. Anyway, let me now move on to give some further detail at this quantum geometric level about states of tensorial group field theories, trying to emphasize the role of entanglement in defining and then dealing with such quantum states. So it's easy to see, and I'm going to show you in the next couple of minutes, that graph structures are in fact associated to entangled tensorial group field theory states inside the Fock space. So it's entanglement that gives the combinatorial information that we associate to a graph.
Sorry, Daniele.
Yeah.
Could I ask a question? I'm sorry, it's
Of course.
on the previous slide, actually.
Yeah.
About the Hilbert spaces being different between loop quantum gravity and group field theory. The fact that the states associated to different graphs are not orthogonal, does it mean that you in the group field theory you're already taking into account a bit of the dynamics of quantum gravity, or it's simply some
no.
kinematical?
This is just kinematical.
So it's due to the
due to the structure of the Fock space.
Symmetry? The permutation symmetry? Or
it's,
no?
well, it's not even that, because you can deal with symmetrized graphs also in loop quantum gravity, but the statement that the way you deal with different graphs not being orthogonal would be the same. So it's due to the fact that the structure of the Fock space is that symmetrized version of a tensor product over vertex degrees of freedom.
Okay. And it cannot be interpreted as some constraint in the framework of loop quantum gravity?
Okay, that's a different story. So the starting point is simply that you can find the Hilbert space for each graph being exactly the same in the Fock space, but that when you consider different graphs, then states are organized differently. In particular, they're not orthogonal. A second step could be if you can find either in some regime or as a condition on the dynamics or as a further condition on special classes of states you want to consider, conditions like cylindrical equivalence that will turn you into a sub-Hilbert space or a particular approximation in which you find a structure much closer to canonical LQG. That's possible, but I don't know. It has not been done, and I wouldn't know at the moment how to do it.
Okay, thank you.
You're welcome. What was I saying? Yes. So in order to see this role of entanglement, let's consider first a many-body wave function for n quanta of a tensorial group field theory. So just n disconnected vertices. Then you can associate to two vertices. So you can find that you can for such wave function, you can say that in fact that this wave function can be associated to two vertices connected through a link if the wave function satisfies a certain invariance, which is nothing else than a bivalent gauge invariance along the arguments for the two semi-links. And in fact, that means that you can enforce a link map that will glue together the degrees of freedom associated to two disconnected vertices along a particular link. And this map, in fact, establishes entanglement correlations between the degrees of freedom on the two subsystems. And you can generalize that to an arbitrary graph by simply acting with a projection operator, a more general connecting map associated to the adjacency matrix of a particular graph you're interested in. So you define such operation that takes a disconnected state, but acted upon by such operator gives you a state which now has the entanglement pattern corresponding to a particular graph that you have chosen when you selected the adjacency matrix. Now, this applies to states in the pre-Fock space because in defining the map like this, you need to distinguish the vertices, and then you have to project by symmetrization over vertex relabeling to really define states in the full Fock space. So the statement is just that graphs arise at patterns of entanglement among tensorial group field theory quanta. But because of that, because they are just patterns of entanglement, they're not super selection sectors, then states associated to different graphs are going to be not orthogonal in general. As I said, you can identify the entangled state associated to the same graph as a subspace of the Fock space, and then show that in fact this subspace is isomorphic to the loop quantum gravity Hilbert space. The scalar product is the one induced by the Fock space. Next, you just very quickly, the vertex labeling can be argued to be necessarily irrelevant because it's sort of a discrete counterpart of different variants. And in the second quantized language, this irrelevance is exactly the implementation of the symmetrization over relabelings, automatically imposed when you second quantize your description of the states in terms of field operators. I mentioned here, but I'm not going to elaborate on this, that you can introduce a distinguishability at the effective level by basically adapting the relational strategy. So introducing additional degrees of freedom that could be understood as matter fields that you want to use as a reference frame, and then pick up particular states where this reference frame select special values, and then you use those values at the effective level as a label for the vertices that then distinguishes them. So it's a bit like introducing through this material reference frame an embedding into an auxiliary manifold. And this can be compared with loop quantum gravity, where the embedding is instead the starting point. But you recover that type of situation at the effective level. More interestingly, the structure of these entanglement patterns in the Fock space is such that the quantum states can be quickly recognized as an example of the entanglement geometry correspondence at some sort of primitive level. Well, there are many things that for people in loop quantum gravity are probably going to be trivial, but they seem not to be trivial for people not in loop quantum gravity. So let me mention them. So first of all, the fact that entanglement gives you topology is basically what I just said, that the topology, the connectivity is just the entanglement pattern between quantum gravity degrees of freedom associated to vertices. There is a primitive entanglement area correspondence simply because the measure of entanglement for each link associated to the graph is in fact proportional to the spin label that we associate to the same link in a spin network basis, which in turn is proportional to the surface area of the dual surface to that link. There is a similar primitive entanglement volume correspondence because the intertwiner label associated to each vertex follows from the gauge projection, which is nothing else than establishing entanglement between the 4 links associated to that vertex. And that label, the intertwiner label, is then proportional to the 3-simplex volume. And finally, and less trivially, one can show that you can reproduce a discrete version of the Ryuta-Kanayagi formula in the language of spin networks by appropriately choosing states with boundary data and internal surfaces whose area turns out to be proportional, or first of all bounded by the number of links that it cuts at in the bulk. Finally, concerning this entanglement, the role of entanglement in these quantum gravity states, given what I just said, it's immediate to notice that the states, as I define them, are a generalized version of tensor networks, which are interesting structures for quantum many-body systems, whose main virtue is they efficiently encode entanglement among quantum many-body in quantum many-body systems. So this is the definition of a tensor network. It's just a bunch of tensors connected or traced with link states. And that's exactly the type of structure we find for our tensorial group field theory states in the Fock space, with the tensors, which are basically the initial elements of a basis in the Fock space, traced by appropriate link maps. And you can identify in the definition of generic state the corresponding second quantized tensor network. And the generalization is in the fact that contrary to what is mostly done in the tensor network literature, we have first of all general link dimension, then we have this discrete counterpart of different invariants, and more importantly, we have both a dynamical combinatorial pattern. We have a nice geometric interpretation at the simplicial level. And farther down the line, we are dealing with random tensor networks with a probability distribution defined by the underlying tensorial group field theory model. Now, this is nice at the structural level, I think, but it's also useful to do stuff with such states. And I mentioned just one application because people could be interested in that. And is the idea of defining holographic maps for quantum gravity states. We know, and Ethera knows even better than me, that you can define, you can associate, you can define bulk boundary maps associated to this type of quantum states whenever you have a graph with open links. The boundary data being the spins and the magnetic numbers on boundary links, and the bulk links being both the spins of internal links, but also the intertwiner labels associated to vertices. Using this separation of bulk boundary, you can reinterpret the definition of the state as being also a definition of a map from bulk data to boundary data by appropriate contractions. And the nice thing is that, oh, sorry, I think there is a part of the formula missing there. Anyway, the point is that combining this definition of a bulk boundary map with the reinterpretation of the states as tensor networks, generalized tensor networks, one can study holographic properties of such bulk boundary maps using tensor network techniques. And I just anticipate some results of work that we are completing with Eugenia and Goffredo. And first of all, one can show isometry of such maps to be realized, which is a property that you would associate to holography, to be realized whenever the bulk is maximally entangled. The bulk degrees of freedom are maximally entangled. Then you can also show that two simple graphs, two simple states, which equal assignment of spins everywhere on all the links in the bulk cannot be isometric. So you need something less, more interesting, less trivial to have holography. And for a generic graph, increasing the range of possible spins increases the holographic character. Further, you can obtain, again, a Ryu-Takanagi formula, also in the case in which you have dynamical spins. And you can also compute corrections to the Ryu-Takanagi formula, Takanayagi formula in this context. And you can further generalize the calculation to the case in which you have superposition of spins, so sums over spins, and also superposition of graph structures, although that is more complicated. Okay. Here I leave the kinematics, the discussion of the quantum geometry as such. And in a sense, I try to leave the microscopic level of description. And I start wondering how I could extract from this class of models based on such type of fundamental degrees of freedom, quantum geometric degrees of freedom, I could extract some continuum space-time and possibly gravitational physics. Now, in general, from the point of view of the models we considered, we should expect continuum physics to correspond to some coarse-graining of the quantum gravity data. So we should resum the lattice data. Also, it should correspond to some form of non-perturbative physics, exactly because it has to correspond to the result of resumming the simplicial complexes generated in the perturbative expansion. To some extent, at least, and at least approximately. And because of both points, continuum physics will correspond to collective physics from the point of view of the microscopic degrees of freedom. So this is a way of re-understanding what continuum path integral for quantum gravity, so continuum gravity dynamics should correspond to the full, ideally, the full partition function for the lattice system. Then, of course, the advantage from this point of view of the tensorial group field theory formulation, I think, is that, again, you get new tools thanks to this quantum field theoretic embedding of simplicial gravity, loop quantum gravity, spin form gravity structures. So we focus on this quantum field theory rather than looking at the spin form definition per se, or the loop quantum gravity states per se. And we realize that the continuum limit of the theory, since it corresponds to evaluating the full partition function, ideally, it basically corresponds to analyzing the renormalization group flow of a given tensorial group field theory model that we are interested in for its quantum geometric interpretation. And we should realize then that fully evaluating the partition function or the effective action for a given model will not give a unique result. We should expect the system to organize itself in different phases depending on the values of various coupling constants. And people have encountered exactly the same issue in all these related approaches: canonical loop quantum gravity, spin form models, lattice path integrals, and so on. Here, I'm going to discuss briefly this issue from the point of view of tensorial group field theory. Okay, and the point is to study the renormalization group flow of the model, of possibly of quantum geometric models. In fact, we have much more experience in simpler models in this tensorial group field theory framework. And to make a longer story short, there is a plethora of models that have been studied with abelian groups, non-abelian, in different ranks, with or without additional symmetries, with different choice of interactions, and so on. And first of all, we know that these models can be made sense of. They can be renormalizable. They can even be shown in many cases to be asymptotically free or asymptotically safe. And the real question becomes whether we can compute the full limit, the full continuum limit. And that's the, from the point of view of the RG flow, is the IR sector of the theory. And again, also here we have a lot of results. I just mentioned the last more recent results obtained by Andreas and Johannes in a nice couple of papers in a rather general analysis of tensorial group field theories in the non-quantum geometric setting. And what they've seen is that as long as you deal with compact groups, you don't really see phase transitions and non-trivial phase diagrams, but you start seeing them if you send the volume of your domain towards infinity, a sort of a thermodynamic limit. And you can find some rather general set of insights that seem to apply to larger class of models. Now, the point here is that on the one hand, we have a lot of experience. That gives us a good basis for studying more complicated models. At the same time, we need indeed to study further models, non-compact groups in particular, and models with matter coupling of the type, for example, that I'm going to introduce in a second for discussing cosmology. But more generally, we know very little about quantum geometric tensorial group field theories. And the reason is simply that they're much more complicated. And in particular, we know some scaling amplitudes, we know some form of divergences, but you basically don't know anything else. We don't have general power counting theorems. And one reason is that we do not control the theory space of such models, without which it's hard to do any proper renormalization group analysis. So before I move on to the next final part about cosmology, I'm happy to answer questions.
Okay, thanks. If I wanted to ask you if how group field theory compares to usual quantum field theory, because at the beginning you said there's a non-locality in group field theory, and so when you do the renormalization group analysis, the non-locality has a big effect in the UV regime or in the IR regime, or it's just totally different from the usual quantum field theory?
Okay, so concerning the UV regime, so concerning renormalizability, I'm not sure if there is a very general statement I can make, beside the fact that the usual, the conventional wisdom doesn't apply. If you were just trying to say, okay, by naive power counting a theory with such order of interaction and such dimensionality of the domain will be renormalizable, or vice versa, will not be renormalizable, well, think again. It doesn't necessarily work like that, and we have counterexamples in both directions. It really depends on the pattern of combinatorics. It depends a bit more on what type of group you're choosing, if you have additional symmetries and so on. Concerning the IR, then I can answer with this general points here. Again, they've been found in a particular truncation, but it's rather general, and it seems to be a rather general validity. So what you find is that, again, there's no phase transition, strictly speaking, if you stay with a compact group, and that's in agreement with what you would expect from local field theories. So from that point of view, the non-locality doesn't change much. If you take a thermodynamic limit, then the tensorial group field theory seems to behave very similarly to a local theory close to the fixed point, to a local theory in an effective dimension that combines the rank and the dimension of the group. But it combines it non-trivially, because you basically always lose a direction at dimension 1. The difference with local field theory is that generically you seem to always have a flow of the anomalous dimension, and that complicates a bit the whole analysis. And what else? Still, you seem to be find nice phase transitions, including Wilson-Fisher type fixed point, at least in the truncations being analyzed and with the caveats due to the various approximations. I hope this helps.
Can I also ask a question? Hi, Daniele.
Yeah, hi, Simone.
Hi. These nice results on the renormalization and especially the phase transition and presence of fixed points, are they obtained for the partition function or also for amplitudes with given boundary data?
I think that so far people have just analyzed the flow or the effective action. In some further analysis, not this one, people have tried to take into account word identities and so on, but still at the level of the effective action alone, not the correlation functions, as far as I know.
And the effective action with some background field dependence in it?
No.
No, okay.
You can do the expansion around like a trivial field configuration in like a local potential approximation, but you don't use any background field method in a strict sense.
So we don't know yet then how to take advantage of these results to kind of infer the truncation that would be sufficient to answer some given question that concerns then an amplitude with given boundary data.
So for these models, as I said, I don't think it has been analyzed, but I'm not sure there is any particular difficulty. The point is that, of course, these are not the type of questions we would be interested in, because the interpretation of the boundary data will be much more trivial than in quantum geometric models. So even if you extend that...
but still the question of whether you need to simultaneously refine the boundary data or you can keep them fixed and find a continuum.
Oh, okay, but this we have some results at the perturbative level. Because in that case, you know, the perturbative analysis has been done relating the degree of divergence, you know, that follows from the combinatories of the boundary and the combinatories of the bulk. So that we know how to relate the two. So we know in what sense, you know, higher complexity of boundary data necessarily translates into a certain higher complexity of the bulk and therefore a different degree of divergence. At the non-perturbative level, I don't think it has been
But
done.
even just at the perturbative level, if there is a different degree of divergence, then does that mean that there's also a different renormalization and possibly different phase diagram?
But you don't see the phase diagram at the perturbative level.
But you might expect it to be.
No, sure. I mean, we know that already. Yeah. Okay. So if that's the question, so we know from the perturbative analysis that what type of data you have on the boundary changes the way the bulk amplitudes flow. So from that point of view, sure. We have no analysis at the non-perturbative level of this relation. And at the perturbative level, it has been accounted for in the analysis of the renormalizability of such models. So it is under control, but only at the perturbative level.
And so when you say that the boundary data effectively change, already you can see that at the perturbative level that they change the degree of divergence, and so the renormalization procedure, you mean all of the boundary data, so both the type of graph and the variables on the graph, or just the type of graph, and then whatever you color it with, it doesn't matter?
Say it again. So the type of graphs, for sure, because you know you have a different combinatories, and
but you might also assign different spins or different holonomies. Could the values of these boundary spins or boundary holonomies or whatever it is in the model affect that too?
Well, it's accounted for in the sense that, you know, when you do the various subtraction procedures for doing perturbative renormalization, of course, if you have data that set for you the scale on the boundary for your graph, and then you have to absorb divergences that are sort of UV from the point of view of the boundary scale. So from that point of view, yes.
Okay, but the different renormalization scheme only comes from having changed the boundary graph, not from the fact that you're.
No, but you don't change the renormalization scheme. The renormalization scheme is the same. If you take a generic amplitude and you ask how does it diverge, and so what type of counter terms I should add and so on, that will depend both on the combinatorics and the type of data you have on the boundary. Some boundary data will not produce necessarily divergent diagram, or they will change the way the diagram diverges.
Okay, this is what is not, okay, I see. So that is the case effectively. So you mean that if the boundary holonomies or spins or whatever, I don't know, are somehow bounded, then there might be enough to prevent some divergences to develop in the bulk or something like this?
Yeah, I think it depends on the model, but a priori, yes. But you need some additional constraints on the way you relate various holonomies in the graph. There could be constraints that, you know, if you fix some of them to be bounded, the remaining ones, which happen to be done in the bulk, are then also bounded. In particular, in the presence of gauge symmetries, this could be the case.
Okay, thank you.
Yeah, you're welcome.
Hi, Daniele. I also have a very quick and naive question. So when you're talking about here RG flow, what's the RG time that you're using to make the flow?
Yes, so you have a field theory over a group manifold. So you normally use the scale as indicated by the Killing form on the group, which is your metric. Or if you want, as indicated by any differential operator you have acting on the group manifold in your kinetic term. So if you have a Laplace operator on SU2, then your scale will be the SU2 spin, or the cutoff in SU2 spin, which labels the spectrum of the Laplacian.
Okay. So you have a cutoff on the Laplacian on.
Yeah, you put some IR cutoff, some small spin, And that's, is the thing that you send towards 0 to get to the IR.
Yeah, perfect. Thank you.
You're welcome. Okay, so if this point is clear, I go to discuss how to extract gravity and cosmology out of this, in particular cosmology. So the idea, as I said, of the continuum, extracting the continuum physics it would be ideally to compute the full quantum effective action. Of course, that's a nightmare and you cannot do it, and you have to do a lot of approximations. The approximation should be such that you capture collective effects from the point of view of the discrete structures that you started from. The simplest such approximation is to just evaluate the full path integral at the saddle point, or the quantum effective action as the classical action of the model you started from. And that's basically the mean field hydrodynamics. Working at this mean field hydrodynamic level corresponds, from the point of view of the quantum states, to working with the simplest field coherent state, which is an infinite superposition of spin network degrees of freedom, but it's like working with a gas of tetrahedra in which you totally neglect connectivity information. So you just treat them as independent, but you superpose over arbitrary collections of them, all weighted, each weighted by the same wave function. So the main point is that the full quantum state encoding an infinite number of degrees of freedom is in fact captured by a single function, which is the condensate wave function that I labeled sigma here. So in fact, in order to extract physics, we will see that a good strategy is to apply the relational strategy. And so we need to work with models in which we have also coupled at least a single scalar field to your quantum geometry. This can be done. Again, the details are not so crucial here. The main point is that the guideline for constructing a corresponding model is to extend the domain of the field to include one extra real variable, and then construct the amplitudes in such a way that they correspond to lattice gravity path integrals for gravity coupled to the real free massless scalar field. So you do that, so you extend the domain of your field to include an extra real number, which is the value of your scalar field. And then you extend field operators, states, and so on. And you can write down an action, which following the guideline turns out to have the following two properties. Because you are discretizing your scalar field at the lattice gravity level in such a way that there is a single value of the scalar field in each four simplex in terms of the lattice path integral, then the interaction of the tensorial group field theory for such couple model is local in the scalar field variables. Second, because you want to reproduce the path integral for the scalar field coupled to discrete gravity, it turns out that the kinetic term has to contain an infinite number of second derivatives of the tensorial group field theory field with respect to the scalar field variable. So you have a rather complicated action, but that can be written down, and you extend what I just said about the condensate state to have mean field hydrodynamics extracted from the theory to the inclusion of the scalar field. Then you repeat the same story. And again, the idea of having the same wave function for all the tetrahedra is that you're somehow implementing a sort of homogeneity, which also matches the intuition of working in this hydrodynamic level of the theory with purely global observables, global quantities. In fact, you can justify this intuition at the more technical level. The first thing is that you can show that the domain of the condensate wave function is in fact isomorphic to the mini superspace of homogeneous geometries for gravity coupled to a scalar field, to a real scalar field. So really, your condensate wave function looks like a wave function for quantum cosmology. Second, the effective dynamics that you extract at this mean field level is in fact literally a nonlinear extension of a quantum cosmology type equation. So you really have cosmology emerging as a sort of quantum gravity hydrodynamics. So the dynamical variable is this condensate wave function, and the choice of initial model enters in the choice of kinetic and interaction kernels that determine the equation of motion for such wave function. There are two things I want to say here is that the equation is nonlinear. So although it looks like a quantum cosmology equation, there's no Hilbert space structure for the wave functions, for the condensate wave functions. Second, you expect this type of mean field approximation to be valid only if the interactions are pretty weak. Otherwise, correlation between quanta should be much more relevant, and you don't expect this mean field to be enough, although you may be lucky. At the same time, interactions will grow with density of the wave function, so you need smallish densities. But at the same time, the density of your fluid made out of this quantum tetrahedra cannot be too small, because if you have a density which is too small, then it means that you're working with very small numbers on average of quanta, and you shouldn't expect, for a different reason, the hydrodynamic approximation to be valid. Okay, then we apply the whole idea and this general setup to a class of models, which is basically the PRL model, generalized in some aspects that I can point out, and coupled to a real massless scalar field. We further approximate to isotropic configurations, basically equilateral tetrahedra, so that your wave function will depend only on a single spin and the value of the scalar field. Further, we first analyze the free theory, so we assume that indeed the interactions are subdominant, which is also good if we want to trust the spin form dynamics, the intuition from the spin form dynamics. Okay, and then we want to use now the scalar field to provide a relational clock. So to recast the emergent dynamics, the effective dynamics for the wave function in terms of relational observables. So we need to assume that we work with states for which the scalar field is a good clock. And that means, first of all, that our condensate wave function should be well picked on a given value of the real scalar field. So we select this particular class of states when this is true, out of which we extract an equation for the resulting reduced condensate wave function. There are a number of parameters which have to do with the initial choice of model on the one end. Those are the A and B that you see there. And they have to do with the specific choice of wave functions peaking on a given value of the scalar field. And those are the other parameters, epsilon and pi 0. You can recast the equation in a more standard hydrodynamic form. In fact, the only thing that matters turns out to be, in the end, the density of your fluid, not the phase. And you have some conserved quantity. In order to give a geometric interpretation to this, we define observables, and the key ones for cosmology here turn out to be what we expect. So the number operator is always there. Then there is the total volume of the universe, which is the sum of the volume contributions from each quantum, the value of the scalar field, and the momentum of the scalar field. These are computed then in expectation value in the class of condensate states I introduced to give us the relational number operator, relational universe volume, the value of the clock, and the relational momentum of the scalar field. In terms of such quantities, average quantities, but computed in the fundamental Fock space in this special class of states, you can extract equations for the volume. Dynamical equation for the volume of the universe, which is the only thing that is supposed to matter if you are in a homogeneous isotropic context. The first thing you check is that these effective equations have the correct classical approximation. So at later times, largish volumes, more or less, you obtain the Friedmann equations for the universe and the identification of a certain combination of the microscopic couplings labeled mu with an effective Newton constant. So here, the gravitational parameters are themselves emergent notions that are functions of the fundamental couplings. Okay, then you can also show that although there are
you said that this identification, you have to do it at some given spin. You didn't say it actually, but it was written.
Yeah, so it happens in two cases. Either one spin dominates at late enough time when you expect the semi-classical approximation, and then it's enough that the identification holds for that spin that dominates.
So let's see. If the spin dominates, basically it means that the sum, you just take one term out of the sum.
In that approximation, yes, in that regime. At the end, only one spin is more dominant than the others.
And then basically you make...
and then the coefficient corresponding to that spin will play the role of the effective Newton constant, and then you get corrections because it's an approximation anyway.
So rho will then be the rho of the dominant, the variable you call rho at that dominant spin is somehow the density of the matter.
No, that's still the density of the quantum gravity fluid.
But okay, but in the regime in which you recover just the standard Friedmann equation.
No, on the right, so this is a standard Friedmann equation in relational time. So the right-hand side is a constant.
Ah, I see. Ah, okay.
So
and then if the other terms in the sum, you interpret them as somehow quantum corrections, maybe?
Yeah, they are going to correction quantum classical, you can call them as you like, but they are corrections because they are by definition subdominant compared to the first one. So you get Friedmann plus modifications.
Okay, okay, thank you.
Okay, otherwise, this is a sufficient condition, as I said. Then a priori, the only thing you need is that in this regime, the whole right-hand side is approximately constant. It could be given by some complicated relation between the various spins, but it's just a more complicated case to study. Okay, then, as I said, you find solutions with a singular behavior, but under rather general conditions, you find a quantum bounce. So the volume remains positive at all times, and there is a single turning point. And you can compute quantum fluctuations and show that remain small for at least a specific range of parameters. Remain small at the bounds. They are generically small in the semi-classical regime, you can show. Okay, let me skip this. Now I want to close with, do I have another 5 minutes? Or?
Yes, sure, please.
Yeah, okay. So I want to close with a comment on the resolution of the singularity in this scenario, and then with some recent results about late time acceleration, if I manage, because well, it would be interesting to mention them as well. Okay, so concerning the singularity, I've just said that we find a quantum bounce like in loop quantum cosmology, at least very similar, but in a priori full quantum gravity setting. But I also stressed that we find it in a mean field restriction of the hydrodynamic approximation and within a condensate phase. It could well be that we improve the various approximations, stay at the hydrodynamic level, but including more quantum corrections and so on, and we still find the bounds. Then great, it means that we have a more solid picture of the cosmological singularity being resolved by cosmic bounds. But again, the hydrodynamic approximation should still hold, and we should still stay within the condensate phase. It could well be that the hydrodynamic approximation breaks down because of quantum fluctuations. And it could be also that due to the same fluctuations, we approach a phase transition of the system. So we leave the condensate phase. In this type of scenario, then we couldn't say that the singularity is resolved by bounds, but just that there is a more radical disappearance of any notion of continuum space-time in the regime that classically would be the singularity. Okay, this I'll skip. And among the various other results that have been obtained, I'll be happy to report on cosmological perturbations, but I want to first finish the paper. Instead, I will report on the effect of the interactions, in particular concerning late time behavior of the universe. I anticipate the general lesson before I tell you a little bit more about the actual results. And the general lesson is that in a scenario like this, in which space-time is emergent, then also large-scale properties of the universe can be traced back to quantum gravity effects, details, well, some features of the fundamental quantum gravity dynamics. And so this points to the limits of validity of the effective field theory intuition and results in this context. Okay, so I simplify the whole story. In practice, one can deal with an effective dynamics for our fluid, for our quantum gravity fluid, after the whole procedure as I described, captured by a simple action as written on the slide. And now we take, in this context, starting from this point, we take a phenomenological approach. We say, let's just assume that we have a general type of interaction made of a quadratic term and two higher order interaction terms of order n and n prime and weighted by appropriate couplings. Now, each mode, although each spin of the underlying fluid, although decoupled from each other, will in general affect the coupling of each interaction. I make some assumption, and then I extract the effective equation for the condensate density in this scenario. It is convenient to analyze the resulting cosmological dynamics to just recast this as an effective equation for the volume in relational time, as I did it earlier. But in terms of some effective equation of state for, call it pseudo matter or emergent matter component of the universe. But in fact, it's an equation of state that captures, as if it was some matter field, all the quantum gravity effects in the dynamics in this phenomenological approach. Then we analyze what happens for this equation of state, effective equation of state in different regimes. Now, there is something that we know in general, so it's structurally the case. If you just look at the free theory, we have a short-lived acceleration after the bounce, and then we have a Friedman dynamics. Moreover, for small volumes, the interactions are subdominant. And so this picture coming from the free theory will be valid for small volumes. But when the universe starts expanding after the bounce, then the interactions become more relevant until they're actually so relevant that they are the drivers of the evolution. But the whole point is that when exactly the interaction-driven dynamics starts depends on the values of the coupling constants, which mode contribute to the effective potential, and so on. To summarize the work of some other friends, we know that if a single mode, just one particular value of the spin, say spin 1 or spin 1/2, contributes and the others are totally negligible, then you find that you can have an accelerated phase after the bounce that lasts long, so a sort of quantum gravity driven or produced inflation, no need for an inflaton field. However, you have trouble with semi-classical physics. So either this expansion, accelerated expansion, never ends, in which case either you can show it's not observationally viable, or it leads to a big rip singularity. So we better hope it's not viable. Or it is followed by immediate recollapse at the end of inflation. And so again, you don't really have a nice Friedman phase. I skip this and I tell you instead what happens if more than one mode contributes. You get a much richer and in fact observationally viable phenomenology. The details, of course, depends on the values of the parameters, which you can classify. The main point is that you get a nice Friedman-like expansion after the bounce, no accelerated phase long enough after the bounce, or no inflation. But then what you can get is a viable model for dark energy at late times, because you get a phantom-like accelerated phase at late times. Moreover, avoiding any big rip singularity. So again, the general lesson is what I said earlier. And now in theory, I would have one more slide. I don't know if I have 1 more minute or 2 more minutes to tell you how I get to this result.
Okay.
Yeah, I'll buy you a beer at some point in the future. Okay, so we have to assume that both couplings are again very small, so that the interactions become relevant at a later stage. So once the universe is much larger, so we find no long acceleration after the bounce. We have a bounce, we have some short acceleration, then we have a Friedman expansion. Then the interactions become relevant and we have 2 modes. You can write down the equations for such mode. And you can consider first the case in which just one interaction is relevant for each mode, and then you can extend it to a second interaction term. What is relevant, it turns out, is the combination of the 2 modes. Depending on which one is relevant and with which contribution at which time, you can find a richer type of evolution for the universe. In particular, assuming that we have just one interaction mode, so one interaction for each mode, say spin 1/2 and spin 1, or spin 1 and spin 4, you can write down the effective equation of state. You can check that there is a bound for the effective equation of state given by a simple constant depending on the order of the interaction. Most importantly, you can show that the maximum, the bound, is reached from below at large volumes. And at large volumes, in fact, only one mode ends up dominating. So you have a less trivial dynamics when both modes dominate, then one starts dominating and you approach a constant value for the equation of state. For n equals 6, you have exactly an effective cosmological constant, but it is approached from below. So you cross the so-called phantom divide or phantom crossing, which is needed for a phenomenologically observationally viable dark energy model at large volume. And then you can show that in fact you get an asymptotic de Sitter universe without any big rip singularity, because the effective energy density of the phantom field remains finite. and it approaches a constant value itself. In fact, the type of model you get is, although purely quantum gravity produced, it coincides with one of the semi-classical models in some phantom dark energy literature. Okay, I am not going to say anything about that, but in fact, when you have two modes and two interactions, you can also do some more engineering and combine them to produce both a quantum gravity inflation and a quantum gravity dark energy at late times. Okay, so the message is what I said, beware of effective field theory, and be hopeful that quantum gravity can also give something phenomenologically viable. We just have to work a bit harder to make it more solid and detailed and understand better what's going on. Thank you.
All right, thanks, Daniele.
I stop sharing.
And so these nice cosmological constructions and predictions, how much do they depend on the specific of the model chosen?
Oh, as I said, in this in deriving this relation, we adopted a much more phenomenological approach. We just need a general type of interactions with, you know, that in the isotropic regime takes that simple form. So it doesn't depend so much on.
But can you translate that into, for instance, I don't know if it was APRL based or Barrett-Crane based, would they all pass this requirement?
Okay, so one feature of APRL that is needed in order to obtain that, which is quite crucial, is that due to the APRL constraints, well, not the specific form of the constraint, but the structure of the constraints, when you go to the isotropic restriction, the different modes decouple. So you get that form with a sum over modes and a contribution for each mode. Okay. That generically will probably not be valid. I think Barrett-Crane would also work, but with Barrett-Crane you would have the other problem that you don't have an SU2 description. So you would have to deal a bit more with the Lorentz structure.
Okay.
So that certainly enters. The specific form of the coefficients, not really. One thing that is crucial is that in order to get this effective dark energy, you get an order of the interaction, which is 6. One of the two at least should be 6.
Okay.
So you can have a, so you could have a 4-simplex interaction, but then there should also be an order 6 interaction, which we expect anyway from renormalization intuition.
And so everything is Lorentzian here, right?
Well, I assume Lorentzian because I assume that I can give a proper interpretation to the data, but I'm working with SU2. Okay. So the Lorentzian structure, like in EPRL, is hidden in the form of the kernel, which, however, in practice for this phenomenological approach doesn't even play such a big role. But without that, I cannot really interpret geometrically nicely all this stuff.
We want an order 6 vertex with tetrahedra as boundaries, right?
Mm-hmm.
So there would be no, if I just had to look at the large spin limit, there would be no Regge behavior associated to such an object. But you don't care about that because
no, it depends on the kernel.
No, I just think in terms of geometry, I don't think there's any polytope that has 6 tetrahedra.
Because you're thinking, yeah, if it is just a single polytope. But if it is the construction of several 4-simplices with that boundary, then it's okay.
But the single vertex, will only...
It depends on the kernel. The kernel could be exactly the summing over all the internal degrees of freedom of several. Okay. That's why I was saying, in fact, we expect it from renormalization, okay, because it should exactly capture the type of divergence that you would get from gluing together 4-simplices.
Okay. Thank you.
More comments or questions or criticism or I don't know, manifestation of enthusiasm.
So along the same lines, so also the inertia parameter, does it play a role here? I guess it's also hidden in the...
Sorry, which one?
The inertia parameter.
No, for the same reason. It doesn't really matter. whatever is the effective potential for a given interaction, it's encoded in those lambda j or mu j coefficients. They themselves will be functions of the immirsi. So of course, if you translate the conditions we find on the parameter into a condition on the parameters they depend on, then you will find constraints on the immirsi parameter, but it's at a later stage. You just need some general bound on the coefficients.
Okay, so no big lesson for canonical LQG or spin forms, or in a sense.
Yeah, I really hope that I would actually hope that it doesn't matter. I would be in fact surprised that this type of large-scale generic features will depend on specific values of the immirsi parameter.
Yeah.
Because here, for example, the type of conditions we find is, I don't know, lambda has to be positive, mu has to be negative, or mu should be larger than something, but it doesn't really matter this precise value. So I would be very surprised if it matters so much for the internal parameters, the hidden parameters, but of course it could be.
So hi, Daniele. Nice to hear
Hi,
you.
Joao.
I just wanted to ask, it's a rather simple question. I'm just curious, you were talking about the whole SU2 stuff. So what goes wrong if you want to use the non-compact groups, something like the Lorentz group or SU11?
In which context? The renormalization stuff?
Yeah, for example, okay, first of all, can you define the group field theory models and the tensor group field theory models using those non-compact groups?
Yeah. I mean, first of all, the models with that correspond to EPRL or Barrett-Crane and so on are all constructed with the non-compact Lorentz group.
Well, okay. I thought you said that you were using the the Riemannian models use the two copies of SU2, right? And then you have
the Lorentzian. Here was the Lorentzian models would use the Lorentz group. For the EPRL, it's possible to map the Lorentz structure to SU2 ones.
Yeah,
and
with a particular choice of gauge.
Sure, the gauge you can generalize it. Yeah, the gauge you can generalize it, but the point is that you can hide the Lorentz structure in the form of the kernels and only deal with SU2 based fields.
But so in the context of the APRL model, and then later modifications by Conradi, this restriction of the Lorentz group to one of the subgroups depends on the causal character of the polyhedron that you're considering, whether it's time-like or space-like, right? So if it's a time-like polyhedron, you would restrict to SU1.
Yes, you're right. I'm dealing with the case in which the tetrahedra are space-like. Okay. Then the specific gauge doesn't matter.
Okay, I see. But what would happen if you wanted to implement these non-compact groups? Is there a problem? Does anything go wrong?
So as I said, for the whole cosmological stuff is what I was telling the others, that most of the details do not really matter, because we are taking this more general, hydrodynamic first, and then even more phenomenological approach, and most of the details luckily do not matter. But the models we could apply that are in fact the Lorentzian ones. We're not, one thing is that it doesn't matter to look at the old details. Another is they present some obstacle to what we wrote. What we wrote would apply to those automatically, because what we use of the kernels is much less than the old detailed information. For the definition of the models is, as I said, I mean, you can write down the tensorial group field theory for the Barrett-Crane, for EPRL, for whatever model with the Lorentz group you like. The point is what you can do with it after you write it down. So the problem is not to write down the model. The problem is to analyze it.
So you get into problems in the renormalization scheme?
Yes, simply because the kernels are much more complicated. Mm-hmm. It's not the non-compactness per se. There are tensorial group field theory models which have been fully, I mean, in some truncations, but analyzed from the functional renormalization group point of view, including fixed points and so on, which were non-compact. But they were abelian, for example, like R, the translation group, and with simple kernels. So I really want to emphasize, it's not that there is any technical, in principle obstacle in taking the EPRL model running the whole
Yeah,
RG machinery.
I see.
It's really that the model is complicated. We wouldn't know how to run the machine because we don't know the theory space in full. We don't know what other interactions we should include concretely, which specific additional kernels we should include. And so we cannot really run the machine, but it's not the non-compactness per se.
Okay. Yeah. Well, thank you.
You're welcome.
Hey, Daniele, can I ask you a question?
Even two.
Okay. In your talk, there was two main bodies of results. There was the renormalization and there was the cosmological evolution. So maybe I missed something at some point, and maybe you talked about the relation between the two. So I had a question about that. Is there a relation between the renormalization group flow and the cosmological evolution? Or maybe should it take into account some renormalization in the quantum regime of the cosmology for early time around the singularity, around the phase transition?
Okay. So as far as I can see, the connection you can find or you can first look for is at 3 levels. So one is that the whole cosmology thing is based on the assumption that you can deal with the condensate states, so that from the point of view of mean field, you can just look at the physics of non-trivial field configurations, understood as the expectation value in some state of your field operator. So you're somehow putting yourself in a phase in which, well, in a condensate phase in which the U1 symmetry is broken and things like this. A priori, you would like, so if we're lucky, you would like the whole renormalization group analysis to tell you enough information about the phase diagram, and in particular to tell you that for the interesting models, such a phase exists with the basic properties that we're using. So far, we're not advanced enough on the quantum geometric models to say that. We have hints of such condensate phase in the simpler models, but not in the full quantum geometric ones. So we proceed by assumption. That's the first type of link. The renormalization group should map the phase diagram and tell you what are the available phases, and then you can try to run the machinery in each of them to see what is the effective dynamics.
So you don't have yet a correspondence between the UV results of the renormalization group flow and the bounce results of cosmology?
Okay. First of all, the issue about phases from the renormalization group point of view will correspond to the IR limit, because it's the full, the full flow, and in the functional renormalization flow, you put some cutoff and then you run towards 0, towards the IR, because it's the evaluation of the full partition function, including long wavelength modes. Of course, in our case, that doesn't have a space-time interpretation, but formally, it will be towards low spins. So, okay, that's the formal level. The renormalization group analysis will give you the continuum theory, will give you the phase diagram, and you should then see if it matches with your assumptions for extracting cosmology. The second point is that in this cosmological analysis, I said, okay, for low spins, we find the bounce. Well, low spins, but in particular, low numbers, low expectation numbers of the number operator, low values of the number operator, so low densities. Now, it would be, the connection would be that where the bounce occurs, so what is the minimal value of the volume, and the size of the quantum fluctuations for the volume at the bounce depend on the coupling constants. And the RG flow will tell you that if you go towards low spins, the coupling constants run. So it's possible that when you flow with the RG analysis towards low spin, you find values for the coupling constants that when you interpret them at the cosmological level correspond to very large fluctuations. So you don't trust anymore the hydrodynamic picture, you don't trust the bounce, and that would be a hint that maybe you're approaching a phase transition instead. And I'm sure there was a third link, but I actually forgot.
Okay, thanks.
Daniele, and maybe I don't know if you can hear me because my computer is more. Perhaps you need to do the whole like full-fledged RG analysis of a model which has quantum geometric information and the meta degrees of freedom, like, I mean, trivially so, but the clock fields, right? That is not available at the moment. I mean, that's what we also would like to do rather soon. But I think
So in fact, this has to do with the question about non-compactness of the group, because on the one side you have the non-compactness of the group, but these more realistic models should also have this meta degrees of freedom we use as reference frames. And technically, they are a non-compact direction for the domain of the field, of the GFT field. And so they may also affect the RG flow in a highly non-trivial manner. So the whole thing, I mean, these all points all have to tie together. It's just that if you want to do analysis for the full-blown quantum geometric models, now, on top of the computational difficulties, there is, as I said, the issue that we don't really know what is the allowed set of interactions. And so we cannot really control the theory space on which we run the RG analysis. So it's a mixture of improving our ability to do the calculations, and all the work that Simone and a lot of others are doing is important because it gives us information of how to compute things. But it has to be directed, I would say, towards really trying to determine what the theory space is at the non-perturbative tensorial group field theory level. But that's my bias, because I'm not sure that the amplitudes, the spin foam level, are so useful to capture physics. But that's just personal bias.
Then I have a question with regard to these results with Shanghai. So how long, like you say, okay, you looked at the case where you have these two modes which allow you to create some de Sitter-like evolution at late times. So, I mean, we know from these more simplified cases that, say, when you start with something wild at early times, relational times, then you become isotropic and you get a single mode evolution. So how much actually do these modes have to coexist, or I mean, like, to get this, because otherwise you lose this kind of nice de Sitter-like behavior. So how long do they need to live together?
So first of all, as I said, you need the interactions to be very weak, so that the early time evolution is basically the one dictated by the free theory. So it's like, bounce, no long-lasting acceleration, and then quickly becomes like Friedman. You still have several modes contributing, because it takes more evolution to more larger volumes to have one dominating over the other. And so you need a situation in which the interactions become relevant before you have a single mode dominance, but late enough that you can first have a Friedman evolution, and you can combine the various parameters so that that's in fact allowed. And then you have a late time double regime. First, you have two modes contributing and having a contribute in such a way that they cross the phantom divide and you go to values lower than -1 for the equation of state. And then it's fine if you achieve that, and you can do it for a large number of, for a wide range of parameters, reasonably wide. After that, then it's fine if one mode starts dominating, because that means that you start approaching, a de Sitter type phase, but you do it from below, so that you're already fine with the observations. Can you hear me? Yep.
Okay. Are there more questions or comments? All right, if not, we can thank Daniele again. Thank you.